Welcome back to a spooky edition of ECE 441A, 541A. Announcements, I guess they're all spooky, aren't they? All of these sessions together. But homework number 6 is due a week from Friday. And I'm going to go ahead and try to put some additional material on D2L, and it's essentially answering the question, which root locus diagram? You can have a pattern of poles and zeros, and depending on their spacing, that's going to influence what that particular pattern or the root locus looks like for that pattern. So you could have, depending on the spacing, two different shapes of the root locus for a similar distribution of poles and zeros. Obviously their relative locations would be different if the patterns are different. So that particular video is trying to get you to think, how can you check or understand which particular pattern you might have. We will not have class on Veterans Day, which is the 12th of November. The following Wednesday we will not be meeting in class, but stay tuned to D2L. You'll probably be getting material for that, and then exam number 3 is that Friday. But the day we do not have class, that Wednesday, homework 7 is due. You have 2 homeworks, homework 6 and homework 7, that are due, and that will be the contents of exam number 3, which is on a Friday, the 16th of November. Just as a reminder, I don't even think I have it yet available to you. Lab number 3 will be due the last day or class day. That's December 5th. I don't know how far out or how you're paying attention, how much you're paying attention to your calendar, but I'm trying to just make sure that you have some of these dates in your mind or on your schedule. Deliverable number 1 is due right before the break on Thanksgiving. That's for the students in 541A concerning their project. And deliverables 2 and 3 will be due again on the last day, class day of the semester. As we've been doing most of this time period when we're talking about root locus, we'll start the discussion with a summary of root locus. Then we'll have a quiz. Since I think the entire class is here, it will be very representative of what the class understands. Then we will continue, but actually that quiz is designed to help us understand why we might be doing or how to do rules 5 and 6, and that's where we will pick up, just as a way for you to know maybe what to expect in terms of answers, or what's the answer in the back of the book. You can look at table 9.3 in the textbook. It has a collection of transfer functions with their corresponding root loci diagrams. You can also really cheat and find the actual root locus for your problem by logging in and accessing MATLAB. You can create your transfer function with the TF function in MATLAB, and now these polynomials are represented as vectors. Hopefully you're comfortable with that, and if not, the book kind of coaches you through how to use MATLAB. Then you can simply issue one command, rlocus, on that system description, and boom, the root locus will appear. You can find particular locations in terms of roots and the gain on that spot on the root locus by doing rlocation find, root locus find. That will now put some crosshairs available on your plotting window, and you can now move your mouse around and figure out, okay, I want to see what is the gain at this particular location. Left click on that point and it will give you the gain to get to that point on the root locus, as well as identify the particular values of the root locus or the location in the complex S-plane that you've clicked on. You can also build and play and do things with RL tool, root locus tool, and SISO tool, single input, single output tool. You can build your plant, you can put in a controller, and it will start generating step responses, root loci, Bode plots, etc. for you within MATLAB, and it can accelerate your thought process, but you want to have the tools to be able to self-check or to think through, what should I be seeing? Am I putting in the wrong information in MATLAB, or is MATLAB actually giving me the right answer based on my understanding of the root locus and Bode plots, etc., and transient behavior? Here are the rules. One is, where do we start and end? The branches of the root locus. How many branches do we have of the root locus diagram? What's the general answer for that? I didn't give you a system, so now I'm looking for a particular relationship. It's the branches of the root locus equal the number of open loop poles. So you're looking at that D of S, and what's the order of D of S? Oh, it's fifth order. Oh, I have 5 branches of my root locus. And you're starting on those open loop poles, and you're ending some of your branches at the open loop zeros. Why am I saying you're ending some of your branches? Some of those branches go off to infinity. And where infinity is located depends on the pole zero excess. If you have a pole zero excess of 2, infinity is at plus and minus 90 degrees. If you have a pole zero excess of 1, infinity is minus infinity on the real line. If you have a pole zero excess of 3, now you have an infinite asymptote going off at 60 degrees, one at minus 180, and one at 300 or minus 60 degrees. So those are the ideas that you can keep in mind relative to beginning and ending locations. You know how to cut your bread. That's rule number 2. That's which line segments on the real axis belong to the root locus, and that you can find by simply standing at a root locus location on the real line and counting the poles and zeros to your right. If you have an odd number to your right, then that's a branch, or that's a segment of the root locus. The asymptotic behavior, you can find the angle and where it's centered by these expressions. Breakaway and reentry points deal with relative minimum and relative maximum of k on the real line, and you can find that numerically. You can find it sometimes analytically by differentiating a polynomial. You can use several techniques for finding these or going through these particular rules. Today we'll talk about the imaginary axis crossing, which hinges on the phase angle condition, the angle associated with G of S, H of S, evaluated at a particular point. And if we're interested in the imaginary axis crossing, now we're walking up the imaginary axis and saying, oh, right here, let's say I'm at J2, what's the angle contributed by all of my poles and zeros in G and H? Is it minus 180? If it is, then that particular point is on the root locus. Angles of arrival and departure concern complex zeros and complex poles. And we'll talk about how we can find the angles that the root locus is departing from a complex pole location, or how is the root locus approaching, arriving at a complex zero location. What's the angle? Is it coming in at 90 degrees? Is it coming in at 135 degrees? What direction or angle is it really approaching at? Here's the quiz that I promised. Given this system, here's a closed loop system which we're now playing with, is the point S equal minus 1 plus J2 on the root locus. Is that location, that particular point in the complex S-plane, is it on the root locus? And that well, I'm tempted to have you give me a thumbs up and a thumbs down right now to see where we're at in terms of our understanding. Are you ready to answer that question? Does it take a lot of effort to determine? Really, I'm asking you to sketch the root locus of g of s and see, is that root locus potentially going through the point s equal minus 1 plus j2? All right, so I'm going to ask you, based on, I know that you're already finished doing this, with a thumbs up if you say it is on the root locus, a thumbs down if it's not on the root locus. So at the count of 3, I want to see thumbs up or down. I guess if you don't know, you can have your thumb sideways. Are we ready? 1, 2, 3. So if it's on the root locus, it's a thumbs up. If it's not, it's a thumbs down. Are we changing directions? Reversing by 180 degrees. We know what? 180 degrees is important. That point is not on the root locus. And how did you figure that out? Here's our S-plane. And how do we begin a root locus plot? We simply start putting poles and zeros down on the diagram, on the S-plane. Do we have any finite zeros in this g of s? So we don't have any open circles. We don't have to worry about that, but we do have 2 poles. We have a pole at minus 1 and a pole at minus 3. And now you can start cutting the bread. You can at least say which segments of the real line belong to the root locus. How many line segments exist now with this pole zero pattern? I'm sorry, how many total line segments do we have? How many pieces of the real line do we have in segments? Does that make sense? If I had a loaf of French bread, how many segments have I cut it into? I cut it everywhere I have a pole or a zero. I've cut it twice, so I have 3 sections of this French bread. The only section that belongs to the root locus is between those poles, 2 poles. Do they just stop? Are we finished? Is that the root locus? What's rule number 3 tell us? That tells us the asymptotic behavior as k gets bigger. So we can think about number 3 dealing with the fundamental angle. And what's our fundamental angle in this case? It's 180 divided by the pole zero excess. And our pole zero excess is 2. So our fundamental angle is 90 degrees. We have something going off at 90, and another branch, asymptote, is going at 270. So we now have asymptotes at plus and minus 90 degrees. Where is that centered? What's sigma sub a? Well, I can cheat, can't I? I can go back. Did you copy this in the hurried time that I explained these rules? Well, you've probably already encoded those in your brain, right? Maybe you're sleeping on these. Did you get enough index cards for these different rules? Your pillow's getting kind of high now, isn't it, from this class? If I come in one day and everybody has a neck brace on, or neck's stiff, I'll know that maybe you're just putting too many note cards under your pillow. My neck, I don't even need note cards for my neck to be stiff. But what do we have? We have sigma sub A equaling the sum of the poles minus the sum of the zeros divided by the pole zero excess. We don't have any zeros, and we know where our poles are. They're at -1, -3. So that's summing those, we get -4 divided by 2. Our sigma sub A is right between those two poles, and that's true always. When you have two poles, and that's it, the root locus will be going towards each other with negative feedback, and then they split right between each other, halfway between, and then they go, one goes up and one goes down. So now we know that we have, there is our root locus diagram for this particular problem. And there's no way that that line at -2 that belongs to the root locus is going through a point with a real value of -1. Is that clear where that deduction came from? So here's the question. How did you decide? Did you sketch the root locus, or did anyone check the phase angle condition? Did anyone look at G and find out what is its angle at -1 plus J2? Can we do that? Here's our sketch of the -1 plus J2 box. We have our two poles indicated at -1 and -3. What's the angle theta P1? What's the angle that that first pole makes in looking or going towards that box? If you had your protractor and measured it, you probably shouldn't have to measure this one with a protractor, but what's the angle from -1 up to -1 plus J2? Do you see that it's just 90 degrees? Theta P1, if you can't, you could say, well, what's the angle of this pole factor, S plus 1, when S is equal to -1 plus J2? You plug in S equal to -1 plus J2, and you're saying, what's the angle of J2? Well, the angle of J is 90 degrees. So theta P1 is 90 degrees. What's the angle of the pole at -3? And now, do you see how I cooked this example up so we didn't have to have our calculator? Our people that even forget their calculator forgot class today. What's the deal? Oh well, he'll hear that on the video maybe, and he'll never forget his calculator again on exam day, which is the 16th of November, right? Exam number 3. Don't ask me when the final is. I think it's Tuesday of finals week, isn't it? Don't hold me to that. Shoot, now it's being recorded. I shouldn't have said anything. What's the angle? What's theta sub P sub 2? What angle do you have to turn through to get from, and these angles are all measured relative to a positive real line drawn to the right of that polar zero. And in this case, we're going up 2 and over 2. That's 45 degrees. If you had to calculate it doing an inverse tangent, you could say, oh, that's up 2 and over 2, and that better tell you that you have an angle of 45 degrees, which you could have found by inspection, I hope. So now the angle of G of S, evaluated at S equal to -1 plus J2, and you could plug this into your calculator if you wanted to. You could put this transfer function, G of S, into your calculator and say, evaluate the angle when S is equal to -1 J2, and it better give you the result that we now come up with. We didn't have any zeros. That's what this is. And now we subtract the angle of theta P1 and the angle of theta P2 to find that the angle that that transfer function makes or contributes or produces at s equal minus 1 plus j2 is minus 135. So what? What does that tell us? It's supposed to be a spooky lecture, so who knows what's going to happen. What are we comparing 135 with? It should be 180 if it's on the root locus, right? It should have been minus 180, and this is not minus 180. That's a little bit away from it, and we knew that already. If you sketched this, ooh, that doesn't even look like it goes up at plus and minus 90 degrees, but it did when I drew it. So these are going at plus and minus 90 degrees. And there's no way that's going through that square at minus 1 plus j2. Questions on that? All right, we're doing good. Let's do another one. Given this system, is s equal to j on the root locus? S equal j. That would be an imaginary axis crossing. Ding, ding, ding. This would be something related to rule number 5. For this particular system, does the root locus pass through s equal j? This one you're going to maybe have to think a little bit more on, but you're going to have to factor that denominator. I would probably pull out a piece of paper. I don't know if I could do this in my head, but maybe I could. But now I do have a finite zero. But I think really you need to be going through not only note cards, but maybe napkins. You need to be doing this all the time. Somebody your friend hands you a napkin and gives you a transfer function on that napkin and says, sketch the root locus. Isn't this fun? So now you sketch the root locus diagram associated with that transfer function that they provided you on that napkin. In this case, what's our transfer function? That's g of s. And what's the picture look like? Here's our s-plane. And now these tick marks are every half. I tried to make this a little bit bigger. So 2 tick marks gives us a unit spacing. But do we have any finite zeros in this case? For this g of s, we had 1 0 right at the origin. Where are our poles located? Are they real? Are they complex? If they're complex, where are they? They're in the right half plane, aren't they? Because our coefficients are not positive. They're present, but they're not positive. I said this was a gloomy day. So now you have poles at 1 plus and minus j1. And now we want to know, does the root locus go through j1? What do you think? Let's see some thumbs. So at the count of 3, we're going to have thumbs up saying yes, the root locus goes through j. Thumbs down, it does not. 1, 2, 3. Some horizontal thumbs. What's the deal? So thumbs up says it does. Thumbs down says it does not. I don't even see some thumbs. Some of you that had 442, I like to see that those thumbs are down. Should be not going through J. If you've had 442, maybe you know why, but what's the root locus of this look like? How many pieces of bread do we have? 1, 2, 3, 4. I can count today. How many do I have? There's a bird in here somewhere. I don't think you picked that up on the audio recording, but isn't that the part of our root locus? What's our pole zero excess? What's our pole zero excess? I'm asking why, so that we can figure out asymptotically what happens to the root locus. Our pole zero excess is 2 minus 1. It's 1. So what's our asymptote angle? What are our asymptote angles? It's just 180, isn't it? So at infinity, we're going off to minus infinity. And as k gets big, one of these branches is going to that finite zero. The other one's going off to minus infinity. Now we have to figure out, how do we get from those poles, how do we depart from those poles and re-enter the real axis on the stable side of the S-plane? Any thoughts? What do we know? Do we know that the root locus does this? Try not to pick up my pencil so that I can erase this with one action. Does the root locus look like that? That messy? No, root loci are pretty smooth. Having a good day now. So, what do we do? Now we pull out our compass. Does everybody have a compass in their backpack? Hopefully you've retracted the tip so that it doesn't poke you when it's in your backpack. But now you can extend the tip, put that tip in the circle at the origin, put the ink or the pencil on the pole and actually create a circle. For this kind of a pole zero pattern, we actually have a circle with this zero as the center of the circle and those poles on the perimeter of that circle. And in fact, what's the radius? What's the distance from the origin to that pole at 1 plus j1? What's Pythagorean say? We have a squared plus b squared, don't we? Square root. So in this case, we go 1 over, 1 up, 1 squared plus 1 squared. That gives me 2, and I take the square root. The radius is the square root of 2, 1.4. And so if I now have a compass, if I have a circle that's a radius of 1.4, where am I crossing the imaginary axis? Am I not explaining this very well? It should be at 1.4, right? Square root of 2. So if I could sketch, which you already know that's not true, but where am I going to re-enter then? Negative 1.4, negative square root of 2. So you've actually, seeing this picture, you don't have to go too many rules deep. You just say, oh, I know this trick. This is just a circle with the center at the or at the 0 and the radius determined by, and we'll calculate that, but that now means that I'm about there. Oh, brother, how am I going to do this? That's supposed to be about 1.4. So that should have been a circle. That doesn't look like a circle, but use your imagination. And if you put a mirror up, it reflects exactly the same curve. So this should be doing, oh, it should look better than what it's looking, but you get the idea. We leave the poles, and now we come in and we re-enter the real line at the square root of 2 negative, and then one goes zipping to the origin, the other one goes zipping to minus infinity for various values of k. Questions on that? Wow, that quiz took longer than I thought. So what is the shape of the root locus? We've already answered, haven't we? Can we move on? What was the angle? Or at what angle does the root locus depart from the pole? That's a good one. Does that even make sense? Does that question make sense? At what angle does the root locus depart from the pole at s equal 1 plus j1? If we go back to the diagram, I'm really asking, if I had drawn this correctly, what's this angle? What's theta sub d? What's the departure angle? If you go into the airport and you look at the screen, arrivals and departures, you're going to see different angles, see cities, I guess, at the airport. But in this class, you have the arrival board and the departure board, and when do those even exist? When you have complex conjugate poles and zeros. Then we're asking, what are the angles associated with that? We want to know what's theta sub d. That should be 135 degrees if I had drawn it properly. But we're going to calculate that in rule number 6. We'll figure out how do we calculate theta sub d. But is everybody clear on what I'm meaning by the departure angle from poles? And obviously everything being symmetric, then we're departing at what angle? Minus 135 from that bottom pole. This is kind of fun, isn't it? Why did I go to graduate school? Because I was drawing root loci. Okay, so rule number 5. No, it really wasn't. But anyway, rule 5, imaginary axis crossing. These are branches of the root locus cross the imaginary axis. Did they in our first quiz question? Did the branches cross the imaginary axis? No, they came together and split and went plus and minus 90. No crossing. Rule 5 didn't even apply. So some of these rules apply sometimes, sometimes they do not. You don't always have to use every rule. In the second one, it did apply. We're wanting to know, or we're dealing with rule number 5, which says branches of the root locus cross the imaginary axis if the phase angle condition is satisfied at that imaginary axis location. If I now scrolled back up, so I'm relying on your memory now, which I assume is much better than mine, but if you go back and you now calculated the phase of those poles and zeros at j square root of 2, you can now draw those 3 angles from the pole, 2 from the poles and 1 from the zero, add those up algebraically, and it better produce minus 180 degrees. What I'm saying is that here, I'm trying to say that at that point, the angle, the net algebraic angle associated with this system should be minus 180 degrees. What's the angle from the 0 to that point? What's the angle from that 0 to j square root of 2? That's straight up. That's 90 degrees. That one's easy to calculate. What's the angle from that pole up in the first quadrant to that point? Is it 20 degrees? Is it bigger than 90? Is it bigger than 180? Isn't it getting close to 180. Is it about 160, 165, something in there? What's the angle from the pole at 1 minus J1 up to that blue dot? I like to actually calculate the angles that are less than 90 degrees and then subtract those from 180. In this case, I would say, oh, I now am interested in this angle right there, but I know I need to take its, what, supplementary angle? Am I using the right trig terms? I'd take that angle from 180 degrees, and that would be theta sub p, or theta p1, whatever I'm labeling it. So the angle associated with this pole down here is really this angle, theta p, let me say 2. And theta p2, I'm saying I calculate that by saying, oh, that's 180 degrees minus, I don't know what I want to call this, theta x, theta sub x. And what's theta sub x? Well, theta sub x I could find by the inverse tangent if I didn't want to measure it with my protractor, if I forgot that. If I now have that, I'm now down below by 1, so, and I'm going up square root of 2. So I have a vertical distance of 1 plus the square root of 2. And what's my horizontal? That's 1. Did I do that right? So that's now the acute angle associated with that theta sub p sub 2. And I would subtract that from 180 degrees. Just eyeballing it, it's maybe 120 degrees. All of those, so we have theta 0, 90, minus theta p1, which is upstairs, and minus theta p sub 2, which is downstairs. Those all should be minus 180 degrees when you algebraically combine them. Is that clear? If it's not, let's figure out how to do that. So we can do this many, many different ways. We could check the phase of our g of s, h of s at various locations on the imaginary axis and see, are we at minus 180 degrees? If we're not, then we need to go up or down if we expect an imaginary axis crossing. Or we could use the Routh array. The Routh array, we know that we have symmetry with respect to the origin. And if we have an imaginary axis crossing, we have symmetry with respect to the origin. In that case, we would have 2. So we would be looking at the S1 row, setting that equal to 0, and then going back up with that gain value k from S1 into the S2 row and finding what the exact value was for that choice of k. So let's look at the rule number 5. J omega axis crossing. Let's check the phase of g of s, h of s at j omega c. And here's the picture that I would create. I was getting very creative, so I started changing my pen color. So I'm color coordinating these angles. We have 3 poles. Are we even asking the right question? Do we expect an imaginary axis crossing for 3 poles? 3 stable poles? Does it even make sense to be thinking about an imaginary axis crossing? If this was our g of s, h of s, do we even expect an imaginary axis crossing for this pattern? And what rule might we pull out from underneath our pillow to arrive at this response or question? Asymptote angle. What's our fundamental asymptote angle? It's 180 divided by the pole 0 excess. 180 divided by 3. 60 degrees. We have an asymptote going at 60 degrees. Sigma sub a is going to be some averaged value, minus P1, minus P2, minus P3 divided by 3. It's going to be somewhere in that region at 60 degrees. Yes, I'm departing into the right half plane. So I will have an imaginary axis crossing because I hope you can see how your bread is sliced. They're the segments on the real line that belong to the root locus. We have two branches going at 60 and minus 60, and one branch going off at minus 180. This guy, he's just leaving us alone. He's going off to minus infinity. The other two come together, break away, and approach those plus and minus 60 degree asymptotes. We're now saying, where might that root locus cross the real line? I'm sorry, the imaginary axis. And we know how to calculate the phase of a pole and zero transfer function, or a transfer function that possesses zeros and poles. We find the angles of all of our zeros, add those up, and subtract all of the angles of the poles. Numerator, denominator. We subtract the angles in the denominator, we add the angles in the numerator. So what do we have here? How would I calculate theta P1 if I wanted to do this analytically? What's theta P1? Or maybe I should finish this up. What is this going to be? Do I have any zero angles? No, but I do have a theta P1, I have a theta P2, and I have a theta P sub 3. I can add those up and subtract them, or subtract them individually, and that will be the phase associated with that particular collection of three poles at my imaginary axis crossing, which I've labeled as omega sub x. How do I now calculate theta P1 if I need those three angles? If you'd sketched this accurately, you could pull out your protractor and measure those angles. Wouldn't even have to do these inverse tangent formulas. And that will be close, pretty close, if not better than, obviously it'll be better than what I'm sketching or drawing. What's theta P1? How do I find that? This is just opposite over adjacent, isn't it? Inverse then in the argument of an inverse tangent. So this is the inverse tangent of omega sub x over P1. We comfortable with where that came from? That will give you an angle. The way I've drawn it, that might be 65 degrees or 70 degrees, something like that. What's theta sub P sub 2? Same structure, just different. The height up is the same. The vertical distance is the same. And theta sub P sub 3? So let's put this into a specific example. Suppose that we now are given a g of s that's 1 over s plus 1, s plus 2, s plus 4. And now we want to determine an imaginary axis crossing. We know it has to cross because we know we have a fundamental angle of 60 degrees. We could calculate the centroid of that. That would be minus 1, minus 2, minus 4 divided by the pole 0 excess, which is 3. So it's minus 7/3 or minus 2 1/3. And it's going up at 60 degrees. That asymptote, if you could quickly locate that asymptote and say, you know what, my crossing's probably not too far away from there. So that gives you a pretty good ballpark as to where you might be expecting this omega sub x to be. Obviously that depends on all of the locations of these, But let's just say that for this situation, let's look at calculating the phase of this transfer function. Here that 4 is my point to examine. This is my point of interest. I'm really just guessing. So I'm guessing and checking at this point. But I can now calculate the phase associated with that particular guessed location. And in this case, I have minus the inverse tangent of 4 divided by 1. I have minus the inverse tangent of 4 divided by 2. And finally, I have the inverse tangent of 4 divided by 4. And if you pull out your calculator, this will be 76 degrees. This will be 63.4 degrees. And this one will be, what's the inverse tangent of 4 over 4? Oh, come on. 45, right? So if we add those up, we end up with minus 184.4 degrees. What were we wanting? 180. Boy, we're pretty close. This is a great day, isn't it? So now we have pretty much figured out where that upper branch crosses the imaginary axis. It almost crosses at 4. What do we really want? Do we want this? So now if you said, oh, I guess I don't have it drawn, but imagine P1, P2, and P3 are at 1, 2, and 4, and now I go up omega sub x is 4. Which way do I slide omega sub x if I've now calculated it to be minus 184 at 4? Do I want omega sub x to go higher on the imaginary axis or lower for the actual imaginary axis crossing? We wanted minus 180. We subtracted all of these angles and ended up with minus 184. So if we made those angles a little smaller, each of them, wouldn't we be closer to minus 180? Is that clear? So we're really trying to, those angles can be reduced if we move that omega sub x down closer to the origin. Not much, but just a little bit. Is that clear? So our actual root locus branch will cross a little bit less than at 4. How could we do this maybe even and get an actual number? Well, we could try approach number 2. And if you remember what approach number 2, I said your memory was better than mine. We said approach number 2 for this was maybe try the Routh Array. Use the Routh Array to calculate the imaginary axis crossing. And how would that work in our example? Our example we had was g of s was 1 over s plus 1, s plus 2, s plus 4. How do we get a Routh array from this? Do we start cheering? We're going to have to cheer earlier this week, I think. The game is Friday, not Saturday. So Friday morning, our cheers are going to have to be even more enthusiastic because it's less than 24 hours away. Right? So now how do we find the Routh array expression, or we're looking for some polynomial that we can use in the Routh array. How do we do that? What's the closed loop transfer function? Cheer! Kg over 1 plus kg. What's the denominator? That's what we're after, isn't it? That's 1 plus k g of s, which is 1 plus k over s plus 1, s plus 2, s plus 4. And what's the characteristic equation going to be? It's going to be the numerator of the denominator. If we put all of this over a common denominator, then it's what's in the numerator. This characteristic equation is now s plus 1, s plus 2, s plus 4, plus k equaling 0. Now we can put that into our Routh array and find the k that causes the S1 row to vanish, giving us symmetry with respect to the origin, and then use that k value in the S2 row to calculate the actual crossing value. Unfortunately, we are out of time. I know that's very disappointing. Everybody's already packed up and gone. I'm just talking to an empty room, but I will continue talking to an empty room and finish up that part of this, and that will be some AC notes, some after-class notes. I'll see you Friday.